First of all, thank you everyone for coming. This is going to be a lot of fun. I really enjoy talking, and I enjoy talking about type theory. I don't get to do that quite enough. So anyway, just to get a sense of where we're all at, how many people here have studied type systems in any sort of formal setting? Okay, just a handful of you. Okay, good. How many of you are opposed to static typing on religious grounds? Okay, a few more. So, all right, good. I expect those of you who are moralists about this to heckle me extensively, because otherwise this will be a very boring talk. The rest of you ask many, many questions. So anyway, I wanted to give a talk about type theory, and that's what this talk is going to be about, because it's a topic which only appears in really two contexts, one of two contexts. Either it is a very dry topic with lambda calculus and formal proofs, and you probably end up writing pages of calc, or it's an incredibly fiery topic that shows up on Lambda the Ultimate and causes people to leave programming language communities. So I'm trying to be not one or the other, because it doesn't have to be a dry topic. Type theory is very interesting. And it doesn't have to be a controversial topic. Okay, part of the problem with modern languages right now is they all do type, well, at least the mainstream ones, all of the mainstream statically typed languages do it really, really badly. I mean, really, really, really badly. So if you're coming at static typing and you're judging it by the mainstream languages, you know, yeah, you're going to hate it. I hate it too. So this is hopefully exposing you to some other options. Just a fair warning, there's a lot of strong opinions in here. So if I offend anyone, come and punch me after the talk. Not during, preferably. We're going to start out by looking at the basic philosophy of type theory. Okay? Because as I said, mainstream languages are doing this wrong. And to understand why they're doing it wrong, we have to go back to the basics, and we have to look at what does type theory entail? What does static typing mean at a fundamental level? And then take that and look at those features, and what does that force us to do at a higher level in terms of the type system? And once we've got that groundwork in place, we're going to look at two different forms of type inference. One of them is local inference. That's a very, very common one. The other one is global inference, which shows up a lot in functional languages like Haskell and SML. So type systems. The very first thing you need to know about type systems, and arguably the only thing you need to know, is that a type system is a proof system. So a type system is a proof system in the formal mathematical sense. And what a type checker does is it runs through your code and it verifies lots of little itty-bitty proofs, okay? Little itty-bitty, tiny, almost trivial proofs. If you say, in Java, for example, string name equals Daniel, the type checker is going to look at that. It's going to look at the left-hand side, and it's going to look at the right-hand side. And it is going to prove that the two of those are equivalent. In and of itself, this is really not very interesting. Okay? String name equals Daniel. Well, you know, you, the programmer, can look at this, and in 5 nanoseconds, you can figure that out for yourself. So clearly, the type checker isn't adding very much value here. But if you take that tiny, almost infinitesimal amount of value that you get from verifying that string name equals Daniel, and you multiply it by 100,000 declarations in your code, now maybe you have something interesting. Okay? Each and every one of the proofs is trivial. But if you multiply them out by a very, very large code base, now you have something interesting. This is where that intuition comes in, that static typing is more useful in enterprise-class software, whatever that means. Presumably, way too many lines of code. So that's where this comes from. And that's where static typing provides value. It's designed to provide a safety net. It's designed to make programming safer and easier for you, the programmer. Okay? It is designed to help you. It's a good thing, right? It's not intended to make your life miserable. If I were a functional programmer, and you know that I am, I would call that a side effect. And side effects are bad. So you know, it's not intended to make you miserable, and that's really, really an unfortunate consequence of the way it's implemented. So let's go back to the basics, and let's look at the two principles that underlie all of type theory. Okay, there are two principles which every type system that's a real type system needs to implement, and every concept in type theory grows out of these. This is it right here. Does everybody feel enlightened? Right? Rule number one of mathematics. Understanding comes through Greek. Yeah, let's translate this. These two principles are called progress and preservation. Now, progress says that if a term is well typed, and a term is like part of an expression, right? You can think of it as an expression or a sub-expression maybe. So if a term is well typed, if you can get a type for a term, then we know one of two things. Either it evaluates one step at runtime, or it's already a value. So either the runtime system will be able to make some progress in evaluating it, it'll be able to take a step forward, or we've already taken all of the steps we can possibly take, and we're at a primitive value, like an integer literal or a string literal, maybe a lambda. We've gotten as far as we can possibly go. Those are the two things, the two options that progress gives us. And this is the property of type theory, which ties static typing to the runtime. So there's this intuition that static typing gives you insight into runtime state, into what your program is going to do at runtime. This is how it happens. This is what makes static typing useful to you, the programmer. Because if you think about it, you only care about what happens at runtime. It doesn't really matter to you what the type checker thinks of your program. All you care about is the runtime. And this is how the static type system tells you something about the runtime. It's through progress. Preservation is the other side of this, and it's also very, very important. So preservation says that if a term is well typed and it evaluates, so we're assuming case one of progress, then the result has the same type that we had when we started. So progress says that a term isn't going to get stuck at runtime. If it's well typed, you're never going to be in this state where you're sort of halfway evaluated, not really to evaluate yet, the runtime system doesn't know what to do, and you get a seg fault. You're not going to get that if you have progress. If you have preservation, then you know that when you evaluate, the types aren't going to change out from under your feet. If you started with an int, you're going to end up with an int if you evaluate that expression. And this is what makes it possible to reason about type systems in a formal way. These two properties right here, put together, they give you soundness, which is something that all real type systems have, and C's type system does not. So don't use C. This is still pretty abstract, though. Okay? So let's look at an example. Here we have a term, name.length. Okay? So we're calling the name method, and that's giving us some result, and then we're calling the length method on that result. And it would be reasonable to assume that the length method returns a string. I'm sorry, the name method returns a string, and the length method probably returns an int, right? Because that's defined on string. So the type of this whole expression is int. And it's not a value. So progress tells us that because this isn't a value and it has a type, we have to be able to evaluate it. So we evaluate this down one step. We're calling the name method. And that gives us a result, string literal Daniel. So we substitute that back in, and we get this expression down at the bottom. This expression at the bottom is equivalent to what we had above. It's just evaluated one step. It still has type int, so preservation is working, but it's still not yet a value. So we'd have to evaluate this again. And eventually, we would get down to int literal 6, right? Because that's the number of characters in my first name. But the type would still be int. Okay? The type is not going to change as we progress down this evaluation chain. So progress and preservation in action. This is the fundamental, these are the fundamental principles which underlie type theory. This is all you need to know about type theory. Seriously. I'm not just speaking as a mathematician here. This is everything you need to know. All of the crazy features in type theory, from existential types to linear typing and higher kinds, everything comes from this. You can derive it all from this. So if you know this, you know everything there is to know about static typing. But if we stop and think about this for a second, you'll notice that I've neglected to mention one very crucial practical fact. You know, I haven't asked a very specific question, and that is, where do the types come from? You know, progress and preservation, they both start out by saying, if a term is well typed, if you can get a type for a term, well, where are we getting that type? For all we know, for all the math says, there's some all-knowing oracle that sits in the volcanic fumes and tells us things about our program. Well, okay, there's nothing that rules that out. So if there's nothing that rules out mysticism and voodoo, clearly there's nothing which forces the typing to be explicit. There's nothing which forces you, the developer, to write types. This is a very, very, very crucial point. You, the programmer, do not need to write types. There's nothing in type theory which forces that. So this brings up an interesting question. Why do languages make typing so explicit? Why do they force you to write types? If type theory says you don't have to, why do these languages say you do? And the answer is laziness. This is not laziness in the functional programming sense. It's not lazy evaluation. It's not laziness in the good design sense. No, this is just plain old-fashioned laziness on the part of language designers. So think about it. When you say string name equals Daniel, when you write that string type, what are you doing? Well, you're giving a piece of information to the compiler. You're giving a piece of information to the compiler that only the compiler cares about. It's going to throw that away before your code runs at runtime. The runtime doesn't care what type of this variable is. You probably don't care what the type of this variable is because all you care about is the runtime. So why are you forced to write something that you potentially don't care about? And the answer is because you're doing work for the compiler. You are coming up with things. You're inferring a type. You're coming up with the type string. And you're giving that to the compiler. This is work that the compiler can do for you. This is work that the compiler should do for you. And the fact that it's not doing it for you is simply a matter of the language designer deciding that his time is more valuable than yours. This is why Java sucks. That's the whole philosophy of the language. So yeah, let's not do that. Let's do something better. I'm sorry, was there a question?
Well, I mean, that's kind of not entirely true. There are plenty of type systems where the inference call is required of the checking call.
So the point, which is a very good one, is that there are many type systems where the inference is more difficult than the actual type checking. And this is very true. And we're going to see this in a second. So some type systems, yes, you cannot do full inference. And I don't get as deeply into that as I would like, but we'll hang out later. So if anyone's interested about that, it is a very interesting point. But in general, the programming languages that we work with and the concepts that we work with are generally inferable. Okay, for the most part. You can at least do better than what we have now. So there is an inference algorithm that we're about to see which works on any type system. There's truly no type system where this algorithm doesn't work, and it always makes your life at least a little bit easier. It can't get rid of all the types, but it can get rid of some of them, and so it makes things much, much nicer. And we're going to see that in just a second. So anyway, type inference. Type inference is a misnomer. Like many things in type theory, it's been misnamed. It's not type inference, it's type reconstruction. Because what we're talking about here is the compiler looking at your code, understanding your code in some deep quantitative way, and then building up your types like Lego bricks, right? It's putting the types together like Lego bricks, and if everything fits together at the end of the day, well, then your program is well typed. So type inference turns type checking into a question of consistency, not necessarily a question of, did you happen to hold the compiler's hand? So I think this is a good thing because it moves the burden of type checking to where it belongs, into the compiler. And there are two possible ways to do this. Well, there's more than that, but there's two possible ways to do this. One is where each reconstruction is very self-contained and very narrow. You sort of put the blinders on, and you're going to look at one tiny little chunk of your program. And only considering information in that tiny chunk, you'll come up with a type. You move on, and you never come back. Another approach is rather than considering one tiny little chunk, you're going to look at a larger chunk holistically. You're going to consider all of the information that that chunk has to provide, and you're going to wrap it all up, and then all of the types inside that chunk are going to get stamped out simultaneously. And if you think about it, these two approaches are actually the same thing. Because one is simply looking at larger chunks. So you've got one that looks at small chunks, one that looks at large chunks. They're basically the same idea, but they have very, very, very different effects on your code. Very, very, very different effects on the language, as we're going to see in a second. So local inference. Local inference is the one that confines its scope to a very, very narrow chunk of your code. And usually that chunk is like a single declaration. So in Scala, if you say val name equals Daniel, we can infer that type, but we're going to do it just by looking at that one declaration. We narrow our focus, and we look at the right-hand side of the assignment, the string literal Daniel. We compute the type, we stamp it on a name, and then we move on. And we never, ever, ever come back to name. It's done, right? That's in the past at this point. So this is how local type inference works. Here's kind of an example, right? So we've got a Scala function foo. And we have three types that we need to infer here. We've got a return type for the function, and we need to infer types for name and len. These are two declarations inside the function. So we'll start with name. We look at the right-hand side of this name declaration. And what we're going to do is we're going to compute this type in place. All right? We're just going to figure out what the type is, and that's going to be the type we stamp onto name. So what's the type of a string literal? Well, it's string. That was difficult. Moving on, right? We've got something a little more interesting here. We've got name.length. So name, we already know what its type is. Name's type is string, because we already figured that out. So we can use that information. We're not changing it, but we're using that information here. And we say, OK, look up the length method on string. Well, the length method returns int. So the type of len is going to be int. Moving on. Now we get down to the final expression in the function. And this is what's going to define the return type for the foo function in general. And printline is a function in Scala that returns type unit. Unit is sort of like Scala's version of void. Anyway, so we've got unit. Therefore, the return type of foo is going to be itself unit. So you see how this kind of works, right? We start at the top and ka-chunk, 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 right down the line. Very, very straightforward, very, very easy, and we never go back. It's a very, very linear, single-pass process. Here's another example. Okay? This is a really simple algorithm, but we can actually do some interesting things with it. So if we look at here, we've got two types that we have to infer. We've got nums, and we've got strs. And if we look at nums, this is actually pretty easy, because we're constructing a list with some int literals. So the type of nums is going to be list of int. And there's some more interesting magic going on here. There's actually a method call. But the result of the method call is going to be list of int. So we know that nums is of type list of int. We're just computing the type in place. Moving on. Now we've got strs. And we look at the right-hand side of strs, and we see that this is a little bit more complicated. Because strs is being assigned the result of calling the map function on list of int. Now, the map function is going to take its function parameter, this thing right here, and it's going to run that function parameter against every single element in the list. And then it's going to return something of type list, where the component type of that list is whatever is returned from this function. So what we need to do is we need to figure out what this function returns. What is the type of this function literal? In order to figure out what the type that map returns is, in order to figure out what the type of strs is. But we can do this just within the context of this single declaration, without widening our focus at all. We can just do it looking at this single right-hand side of the equals sign. We start out by looking at this parameter type here. This function literal has a parameter I, and it doesn't have a type on it. But we can come up with that type by looking at map. Map says that whatever function type we give it, the parameter type of that function has to be int, because we're calling map on a list of int. So clearly every element invoked on this function is going to be an int. Once we know that I is of type int, we can figure out the I.toString really easily. It's going to be of type string. So the type of this whole function is int to string. And with that information, we know that map is going to return something of type list of string. So this was a little more complicated. Okay, we had to think about it a bit. But we were still able to do it with just the information contained in a single declaration. We didn't have to look around the program. We didn't have to put a stub type in there and then come back to it. We were able to figure it out right in place. And this is one of the advantages of local type inference. Yes?
Instead of saying toString, that said toReal, how would you know?
Well, we would have to look on int. And we'd see, OK, what does the toReal method return? Okay? Now, there isn't a toReal method in Scala, but if there were, we would look at its return type, and whatever its return type is, that would then be the return type of the function parameter. So toString returns a string. toReal might return a double. So then the result of strs would be list of double. Got it? Yes?
What if you return a different value based on what your input is? You say if I is greater than 10, return I.toString. If it's less than or equal to 10, return .toReal.
That's an excellent question. So I'm going to give you a short answer now because we're going to get to it a little bit more deeply later. But if you have a conditional, okay, an if-then statement, that the two different branches return two different types, then you have to find a type which encloses both the if branch and the else branch. A type which is above both of the two types in there. So you said one returns string, one returns double. We have to find a least common supertype between those two branches. And in Scala's case, that's just going to be any. It goes all the way to the root of the type hierarchy. Anyone else? Good question. Very good question. So this algorithm has a very, very intuitive results. Okay? It's very easy to just run the algorithm yourself and see what's going on. Okay? Not difficult to do at all. So the result is pretty intuitive. You know, we can figure out what the compiler is going to do here if we have to. It's also very simple to implement. Very, 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 very simple to implement. And this is why. If you think about the Java compiler, okay? How many people know that Java doesn't have type inference? Right? It's just not doing it. Well, okay, generics, and in Java 7. So I point that out in a second. So anyway, Java 6 doesn't really have inference. The Java compiler is going to be doing all of this work, believe it or not. So if you look at the expression string name equals Daniel, here's what the Java compiler is going to do with that. It looks at the left-hand side, and it sees string. It says, aha, name is of type string. That's interesting. Put it on the shelf. And then without looking at that information at all, it's going to look at the right-hand side. And it sees on the right-hand side, it computes the type of the string literal. And it sees string. So the right-hand side is of type string. It takes that information, takes the information you gave it for the left-hand side, and it just does a comparison. So the only difference between what the Java compiler does and what the Scala compiler does is Scala doesn't have any information for the left-hand side. So after it's done computing this type, it just puts it on the variable. That's the only difference. Any compiler for any statically typed language is going to have to do this work at some point. So it's really, really, really easy for them to implement it. If you want to implement local inference in your statically typed language, you will spend more time modifying the syntax than you will spend modifying the type checker. It's that simple. And of course, because it's that simple, it's going to be very fast. It's just a constant time overhead on the work that the compiler is already doing for the type checker. And it always, always, always gives you an answer. Always. But even with all of these simplicities, right, it's such an easy algorithm, it still helps a lot. You know, we saw on those previous slides, I was writing code there, and I didn't have to put any types in whatsoever. None of those examples had any types, and the compiler still figured it out. So, you know, that's a big win. Java would have forced me to write a lot to get those previous slides. So this really, 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 really helps. And honestly, I don't think there is any excuse for a programming language designer, for a statically typed language, not to include at least local inference. It's so simple. It's so simple. It doesn't impose any constraints on your language. You can always, always, always do it. There's just no reason not to, unless you want to make programmers' lives harder. So, you know, there's no excuse whatsoever. And fortunately, a lot of languages seem to be agreeing with me these days, because we've got Scala, we've got Go and Mira. Even Java, in Java 7, includes a limited form of type inference that just works on generics. So this is catching on. Finally, it's catching on. And it's getting better. But as you would expect from such a simple algorithm, local type inference doesn't solve everything. There are places where local inference falls over. And this is one of the canonical examples. So this is a function that takes a parameter x, and it adds the integer 5 to that parameter. So we have two types that we have to infer here. We have to infer the parameter type, and we have to infer the return type. And we start out with the parameter type, because we're going to need that, right? And we're going to play our trick of narrowing our focus to just the declaration. And then we're going to look on the right-hand side of nothing at all. This is a formal parameter. We don't have any right-hand side to our declaration. So we could sort of go hunting through the code for all the places where you call this function. But, I mean, you can imagine that would be a nightmare, right? So the local inference algorithm gets here, and it can't do anything. It's stuck. It cannot come up with parameter types. Local inference can never come up with parameter types. And so you always have to annotate them. In Scala, as any other language with local inference, you always have to explicitly annotate your parameter types. And that, it's a little bit troublesome. But that's not the end of the story. Here's another example, maybe even a little bit of a surprising one. So this is the factorial function. And we've dutifully annotated our parameter x. You know, we've told the compiler that it's of type int. All we have to figure out here is just the return type. And so we're going to do that by looking at both branches of the conditional, the if branch and the else branch. And the if branch is almost trivial, because we've got an int literal, so it's going to be of type int. We stamp that on there, and then we move on. We have to compute a type for this else branch here. Okay, we have to figure out what this is, because it could be something bizarre that we'd have to, unify with the if branch, and that might be a little bit weird. So we look at x. X is of type int. Int defines this tar operator, the multiplication. But we have to figure out what the type of its parameter is. What is the type of fac of x minus 1? Well, fac of x minus 1 is the type of the thing that we're currently working on. So this is a problem, because for recursive functions, the local inference algorithm will be recursive. And naively, you just loop forever. It's pretty easy to just throw in a check. I mean, you almost have to do this anyway for type computation. But it's recursive. And this doesn't change the fact that we're not going to be able to come up with a type for this. So recursive functions in languages with local type inference always need to have explicit return types. And for a language like Scala that encourages recursion, this gets really annoying really fast. So it would be nice if we could do better. It would be nice if we could just take a little bit more information into account when we make decisions about types. And the algorithm which does this is global inference. Now, unlike what the name implies, global inference does not look at the whole world. It doesn't even look at the whole program. Global inference just looks at a very specific scope that's larger than a declaration, usually a function. So it looks at one function at a time, and it's going to use all of the information in that function, and it'll use that information to figure out all of the types there, stamp them on, and then move on to the next function. So it's sort of the same principle as local inference. We're just looking at more information all at the same time. So let's see how global inference handles our factorial example. Unfortunately, Scala doesn't have any sort of global inference algorithm. And as we're going to see in a bit, Scala cannot have any global inference algorithm. So we're going to use a language which does. And I chose to use ML. You could use Haskell, but Haskell has some complications. ML is just easier, right? So this is the factorial function in ML. And what we're going to do is we're going to look at this function. We're going to run ML's type inference algorithm. And we're going to see if this can come up with a return type for us. That's all we're asking, just a return type. So we start out by defining a constraint set, sigma. Now, we need this because what we're going to do is we're going to look over the entire function, and we're going to come up with, we're going to discover what are the constraints that this function imposes on these various types. What sort of things is this function expecting from these types? And we need a place to put that. So we've got this constraint set, sigma. And we start at the top, and we're going to start with the factorial declaration itself. And we see that we don't have a return type on factorial. So what we're going to do is we're just going to make something up. That's kind of the idea here. If you don't know, punt. Factorial takes an int, we know that, but we don't know what it returns, so we make up a meta variable a. So fac is a function from int to a. And hopefully, we will be able to come up with some constraints which allow us to fill this in later. We'll come back to this at a later point and fix it up. So we look at, just like with the Scala example, we're going to look at both branches of the if. And as in Scala, ML defines int literals to be of type int. It would be very, very strange if they weren't. So the if branch is of type int. And this is actually enough information to let us be done here. But for instructional purposes, we're going to look at the else branch. So the else branch is the same expression, x times fac of x minus 1. And we know what x is. X is an int. And we know what fac is. Fac of x minus 1 is an a. This is the advantage to sort of stubbing out our types beforehand, coming up with this meta variable. Because now we're not stuck. Now we can actually say that fac of x minus 1 has a type. But the only way we're going to learn what that type is by looking at the times operator. So the times operator has this type, int cross int to int, which is ML speak for two parameters of type int returning type int. So two parameters of type int. The left-hand side has to be of type int, check. The right-hand side has to be of type int. And this is where we make our discovery, that if the right-hand side has to be an int, that means that a was secretly an int all along. So we take that knowledge and we put it into sigma. We put this into our constraint set. And now we've reached the end of our function. So we're going to go back to the top, and we're going to substitute back in for the places where we made up types. We're going to solve this constraint set, and we discover that factorial takes an int and returns an int. There we go. We just figured out the type for a recursive function. Yes?
How would you do that with, let's say, two mutually recursive functions that are naively implemented to stack overflow? And just directly call each other.
So the question is, how does this handle mutual recursion? And the answer is, this algorithm does not. That's a very, very critical point. ML cannot infer mutual recursion. OCaml can. Haskell can as well. But they punt. Okay? They come back to it later. And they do a larger second inference step. It's hard to do that. Yes?
How would you infer a type on something that doesn't ever actually return, that just recurses infinitely? This is kind of like this question, but instead of mutual, just a simple recursion. For example, something that's going to, like a game loop, for example, it's going to just keep running, or server loop.
That's a good question. So what do you do with an unbounded function? A function that never returns, never gives you any information about A. So if we just had fac trivially call itself, what would the return type be? And the answer is we can make the return type anything we want. You know, any answer is valid because no value is ever going to go into there. And so what this algorithm is going to do is in that case, the return type would be A. But we just made A up. So I'll explain what we do in that case in just a second. But there is an answer for it. It does happen. So anyway, we inferred a type for factorial. Given the parameter type, we came up with the return type. But can we do a little bit better than this? Can we, for example, get rid of the parameter type? So we look at this snippet, and this snippet doesn't have any static types in it at all. If you didn't know any better, you would think this was from a dynamic language, because there's no mention of static typing. So the question is, can we make this work? Because this is sort of the holy grail, right? We want to not have to care about static typing, because that's a compiler thing. So can we make this happen? Well, let's see. We start out with our constraint set sigma, just as we did before, and we stub out the types for factorial. Now we have x being of type A, the parameter is of type A, and the return type is of type B. So these are meta variables. We just made them up on the spot because we didn't know any better, and we'll come back to them later if we can figure it out. And just as before, we can look at several points in this function to figure out this information. Factorial is kind of nice that way. But we're going to skip all the way to the end and assume we were very naive and hadn't figured anything out by this point. X is of type A. Fac of x minus 1 is of type B. So we've got this information here. Just as before, to make any progress, we have to look at the type of the star operator, times. It's still of type int cross int to int. So the left-hand side is of type int. The right-hand side is of type int. That means both A and B need to be of type int. Yes?
How do you know it's that star operator, not the one that takes double cross double?
You guys are asking really, really good questions today. So ML doesn't know. ML cheats. And it says that star is defined for both int and real. But if you don't tell me which one it is, I'm going to assume you meant int, because I don't know anything else to do. Haskell has a solution for this, and it's called type classes. And so it basically says that the star operator is defined for any type which is a number in some sense. I wanted to explain that, but I didn't have time. And Haskell can infer it, but it's much more complicated. So very, very, very good questions. Yes?
So the x minus 1 is never looked at. The whole expression is just looked at. Or is there ever a check to see what the parameter is of an inverb?
The question is, do we actually look at the type inside the parameter there, x minus 1, that we're passing to fac? And the answer is yes, we do. That's one of the many places we could have looked in the function to figure out what these types are. We didn't look because I'm sticking my head in the sand. So, because I control the talk. So, but yeah, ML would look at it. And ML would figure out a lot from there. Anyone else? OK. So anyway, A is of type int. B is actually an int. So fac must be of type int to int. So we just figured out the type of the factorial function given no information from the user. Nothing at all. When I first saw this, when I first discovered ML, I was astonished because we get static typing. We get all this safety, but we don't have to tell the compiler anything. The compiler just takes care of it for us. This is real. I think this is amazing. I love this so much. But of course, if our type inference algorithm only works on factorial, that doesn't help us a lot, because how many people here write factorial in your day job? So let's look at a different function, something maybe a little less contrived. This is the grow function. Okay, and this function, it's obviously less trivial, and it's kind of interesting in its own right. I mean, you can use this to define the Fibonacci numbers backwards. Okay, maybe it's not so useful, but you know, it's at least the type inference is going to be more useful. So we start with our constraint set sigma. And we start punting on types that we don't know. F is of type A, X is of type B, And the whole function is going to be of type A to B to C. The return type is of type C. We don't know what that is yet. And so what we have to do is we have to glean information from the function body, just as we did before. And we'll have to actually look at everything this time, rather than just one tiny corner of it. So we look at this function application, f of x. And we don't know what f of x is, because we don't know anything about f. So we're just going to say that this function application just returns d. We're making up a whole new variable, where we're not really making any progress at all, except for the fact that we learned something about f. Specifically, we learned that f is a function that takes a b and returns a d. So that's something we can put in our constraint set. F is a function. And we don't know what it returns. We certainly don't know what it takes, but we know it's a function. So we learned something. Now we have to look at the only other part of this function, which is the cons operator, that double colon there. So the cons operator has this very interesting type, d cross dlist to dlist, which translated from ML means it takes two parameters, one of type d, the other of type list of d, and it returns list of d. So that's what the cons operator does. So the left-hand side is a d. We already knew that. The right-hand side is a d-list. So b has to be a d-list. Furthermore, the cons operator returns a d-list, so c also has to be a d-list, because we're returning this result. So b and c map to d-list. We can put that into our constraint set. So we made it to the end of our function. We walked all the way down. What have we learned? Well, we've learned that metavariables proliferate. We have to look at this a little bit more. Okay? We can't just substitute in for A, B, and C because we've still got variables going on here. We're not quite done. So what we have to do is we have to take a page from the prologue playbook that Bruce talked about, and we have to solve this constraint set. So we look at the constraint set, and we see that there's this thing here, B. And we know something about B. We learned something about B after we put it in the constraint set. Specifically, we learned that B is a d-list. So what we're going to do is instead of having A mapped to B to D, a function from B to D, A is going to be a function from d-list to D. So we solved the constraint set, we substitute in for B, and now we're one step closer. We got rid of our B on the right-hand side of the constraints. But now we're sort of stuck. So we don't know anything about D, but it's still showing up on the right-hand side of our constraints. So does this mean that our algorithm has failed? Were we unable to come up with a type for this function? And the answer is no. We can do this. In fact, the type is a function that takes a function from d-list to D, and then takes a d-list and returns a d-list. So we just substitute in for A, B, and C, including D, and we're there. But this is a little bit weird if you think about it, because D is a variable. We just made it up. We made it up because we had no other information. So why is it showing up in the type? And the answer is because there are no constraints on D. D can be anything we want. Just like in the trivial recursive case, D can be anything we want. So we can make it an int. We can make it a double or a string. But why would we? Why not just say that D can be any type? And at this point, this should be reminding you of a very contentious feature in Java 5 called generics. So if we define this function in Scala, it'll have a type parameter D. And for all D, it will define the function. For any type D, this function is defined. So this is called parametric polymorphism. And this is actually a very, very profound moment, because we should be realizing here that parametric polymorphism is a feature of the type system. It's something that the type system is offering us. It's a way of adding some expressivity to the type system. But we didn't start out asking for parametric polymorphism. We didn't start out designing a language with parametric polymorphism. It just came to us out of the heavens from our type inference algorithm. So this is really, really kind of weird. Our type inference algorithm is so powerful that it's starting to expect things from the type system. It's starting to give us features, specifically parametric polymorphism. Yes?
Do you have to specify the return type there?
Do I have to specify the return type? No, I do not. Scala would be able to infer the return type here, but I wanted to specify it just to be really clear. So anyway, if we follow this idea of the type inference algorithm giving us features for the type system, if we follow this to its logical conclusion, we get something called a Hindley-Milner type system. And the algorithm we've been running actually has a name to it, because everything in mathematics has a name to it, sometimes several names. And the algorithm is called de Moss-Milner. So this is a slight misconception. Most people think the algorithm is Hindley-Milner. It's not. Hindley-Milner is the type system. And a type system is just a set of features, a set of things that the type system offers that the type checker is going to look at. And in this case, that set of features is implied entirely by the type inference algorithm. So where am I going with this? Well, there's something interesting we should be noticing about de Moss-Milner, just as an algorithm. Specifically, what sort of information is de Moss-Milner giving us? It's not really giving us the types, is it? It's just giving us the constraint set. And we solve the constraint set, but we still don't really have types per se. We just have the structure of the types. We have what sort of things those types have about them. What have we learned about them? So de Moss-Milner is giving us structure, not name. In Java, all of your types have names. You define a class foo, okay? And that class has some type associated with it, and its name is foo. De Moss-Milner doesn't know anything about what you happen to label a type. All it knows is what properties is the function expecting from the type. So de Moss-Milner is a structural algorithm, not a nominal algorithm. So any type system which uses de Moss-Milner inference, any type system which tries to do non-local type inference, anything larger than the scope of a declaration, any such type system will end up being structural. You are going to have structural features because just by definition, de Moss-Milner doesn't care what the name is. All it gives you is the structure. So what does this mean for things like Scala? Okay, so I'm saying right here that Scala can't have it. Well, why is that? Well, let's look at Java. Okay, because Java is a very important language because Java's type system influenced the type system of the JVM. I mean, not everybody knows that, but the JVM has a type system that it enforces to some degree. So here's a snippet of Java. And we've got two interfaces, foo and bar. And foo and bar both happen to define the same method. There's a length method that returns int. So given this, we know that something about foo and bar, right? If we have something of type foo, that something of type foo is going to define the length method. It has to define the length method. And if we use that thing of type foo, the only thing we can be using is the length method. And the same thing goes for bar. So if we have something of type foo, can we assign that to a declaration expecting type bar? Does that last line work? And the answer is no. In fact, you can't even insert a cast to make this work. The JVM will fundamentally reject this. Will always, always reject this because the JVM is looking at the names of foo and bar. It doesn't care what's inside foo and bar. It's only looking at the names. And it sees that the names don't match. They're just not related. And so it doesn't allow the assignment to work. So this is what's called nominal typing. It's type equality based on name, not based on what the type is. So it's a much more restricted form of type equality. Because, that foo and bar thing, that really should have worked, right? Intuitively, that should have worked. And it's just this artificial property of the type system, comparing based on name, that made it not work. So nominal typing constrains things. And the JVM is a nominal type system. And so this is a problem. Structural typing is really nice. In fact, structural typing is exactly what dynamic languages mean when they talk about duck typing. So if you think about writing a function in Ruby, right, and, or any dynamically typed object-oriented language, your function takes a parameter, and you're calling some methods on that parameter, and you're not saying anything about the type of that parameter. In fact, you're not even thinking about the type of that parameter. You're only thinking about what sort of methods does it implement. This is duck typing. This is also structural typing. If you run the DeMoss-Milner algorithm against a function in Ruby that's doing that sort of thing, it'll come up with a structural type for that parameter. It'll say that whatever the type of this parameter is, it has to have these methods. It won't give you the name. It'll only give you the structure. Now, of course, if we were to have a language like this that only worked with the structure of types, not the name, then there are some problems which arise. So one of them is the error messages become horrible. Like it or not, things go wrong. Okay? We make mistakes, and sometimes our code just isn't internally consistent. And at that point, you need to get a type error if you're in a statically typed language. And if Java gives you a type error, it tells you something like, expected foo got bar, right? Well, what happens if your compiler doesn't know what the names of any types are? Well, it has to print out the entire structure. It has to say, expected something with a length method, and a size method, and a this, and a that, and the other thing, and got something with these methods. And you can imagine this could be pages and pages and pages of error output, rivaling the C++ template library. The error messages are really, really verbose. But honestly, I think this is a solvable problem. Okay, this is a problem today. If you've ever worked with OCaml, you'll see this. But I think it's a problem that can be solved. It's a tooling problem, not something that's fundamental in the paradigm. And there's another problem that it's not Java compatible. I mean, as I said, the JVM's type system is nominal. And all of the JVM ecosystem, all of these frameworks out there are expecting nominal polymorphism, not structural. And so, if you want to interoperate really cleanly with Java, you can't really have a structurally typed language. And JSR 292 solves some of this. It at least makes it run fast. But it's not going to completely solve the interop problems because just the libraries weren't designed for it. The APIs aren't there. So we've got two problems here. Okay? Two problems that are holding us back from type inference nirvana. Right? We've got this goal that we want to never be able to write, we want to never be forced to write static types. Never be forced to annotate our types. And DeMoss-Milner, global inference is the way we get to that goal. So we've got two things holding us back. Number one are these really, really, really verbose error messages. That's a tooling problem. Somebody much smarter than me can come up with a solution. I have faith. Number two, Java compatibility. We can't do Java compatibility and have a language with global type inference. That's not going to be a problem forever. Okay, Java is huge. Java will always be huge, but it's not always going to be as huge as it is now. Think about C. C was enormous in its day, and it's still really important, but we don't tie ourselves to C compatibility anymore. We will not always be tied to Java compatibility. So these two things are solvable. We can overcome these. And if I can just get up on my soapbox here, when we overcome these, statically typed languages of the future will use structural rather than nominal type systems. Because the advantages are just so clear. We get we can have global type inference, and the polymorphism is so much easier. We get safe, statically checked duck typing, all of the flexibility that it entails. So this is the future right here. I don't know how long it's going to take, but this is what it's going to look like. I'm very, very confident of that. So in conclusion, we're kind of coming to the end here. Type systems do not have to be horrible. I think if you slept through the entire talk, this should be the thing you zero in on now. Okay? Type systems do not have to be horrible. We can do it better. Don't judge static typing based on Java. I hate Java too. So just don't make that assumption that it all has to be as bad as Java is. Number two, there is no excuse for a language not to have local inference. None at all. It's just so easy to implement. I mean, sometimes you can't implement more complicated algorithms like global inference, more powerful things like that, but you can always, always, always implement local inference. Number 3, inference can have a very, very profound effect on your language. We saw how DeMoss-Milner inference gives us structural typing and parametric polymorphism. You know, these more powerful inference algorithms, they start to require things from your language. So this is something that's very important to understand about why Scala doesn't have global inference, why Scala will never have global inference. And finally, nominal typing is bad. Don't do it. Nominal typing just makes things way, way, way too hard. And you know, I think in the future, we will get beyond this. We won't be shackled to it forever. So yes, any questions?
Just, you know, C++ has some amount of structural typing. For instance, you can do type tabs like, you know, to ints, and you can interoperate. You know, you can supply, you know, let's say type that foo equals int, and type that bar equals int, and you can pass a foo in place of bar, which is structural.
So the point is structural typing and C's type defs. That's not actually structural typing. It's type aliasing. And there's some polymorphism there, right? So the type alias can point to any type you want. But C is going to resolve that statically. And it's just going to substitute in an int or a double or something like that and make that comparison based on name.
Well, I mean, it's actually worse than that. It's actually weak typing.
Oh.
C though.
C++ has that too. That specific feature typeness.
Right. So I'm saying like in C++ take a struct and you know, have two different fields and type that way, and you could interrupt. You could supply two different type sets. Potentially was supposed to be a new type, but then you can supply different types and it'll work. But in other places it ignores it, so it's inconsistent.
Yes, so the point is that the structs in C and C++, you can sort of be a little bit polymorphic with the way that goes. And you know, by casting through the void pointer, for example, you can make that happen as well. But that's one of the many reasons I claim that C's type system isn't a real type system. So that's one of the things that causes it to break.
But my point is like C++ doesn't implement it in its purity, and therefore it's breaking the consistency in the model. But it does have structural typing.
Yeah, it does have a weak form of structural typing, yes.
So in terms of your drawbacks for global inference that you talked about, it seems like there's a third one you did mention, which is that if you make an error defining your function, you might not get an error message at compile time. You might rather have generated a function with some crazy type that you weren't expecting, and you won't notice that until you go to use it, and then later on everything kind of explodes. I mean, do you think that's actually an issue or not? I mean, what's your feeling on that?
So the point is that type inference, just in general, if I can generalize your point a little bit, type inference in general moves the error point, the point where you get the error message. It moves it away from where you made the actual mistake. That maybe is a problem. I've argued in the past that that is a problem. Now I'm not so sure, because static typing is in a sense just an exercise in consistency. Do the Lego bricks all fit together? You know, if they all fit together, what do you care where the things fell apart? And so it makes it difficult to track down the source of an error, a type error. I'll agree. But I think if you start out with the assumption that you, the programmer, know what you're doing, and your errors are going to be infrequent, then I think in the end it's a good thing, because the advantages are manifest. I think, yes?
A few Scala questions. First, so in Scala, you have to specify the return type of a method that uses the optional return keyword.
Yes.
And then I was wondering why that was. My other question is, I wonder if you could just comment on what's called structural types in Scala.
OK, so there were two questions there. One is about structural types in Scala. The other is about inferring return types for Scala functions that have explicit return. The fact that Scala doesn't infer return types for explicit returns is partially laziness, partially just safety. Because there are cases you could get into with an explicit return that the compiler, I mean, it would mess up local inference and it would be very surprising to the user. For example, Scala, this is horrendous, but Scala allows you to do non-local returns. So you can pass a lambda and then return from that lambda. And what's the type inference going to do with that? Maybe you ended up with recursion without even knowing it. So that's really why that is. As for structural types in Scala, they are very, very weak. They're very, 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 very weak. They're just anonymous interfaces without open recursion. And so they're not powerful enough to support this sort of language feature that we want with global inference. Yes, Stuart, I think, and then we'll come back to this side.
How does the presence of null in Java affect Scala's type system?
So yeah, how does null affect Scala's type system? Null in Scala is encoded as a special case of the bottom type. So this is coming back to the question of inferring a trivially recursive function. The correct thing to do for the return type on a trivially recursive function is the bottom type, the type which represents all values everywhere. Null sort of has that type because you can substitute it anywhere. Yes?
So with structural type inference, you're comparing the structure of two things to determine if they're equal, right? Two types to determine if they're equal, right? And so your reasoning for why it would be impossible to do that with a language like Scala that's built on the JVM is that the JVM uses nominal, uses names everywhere to compare, right? So wouldn't it be possible to build a language where you created types that were named based on the structure, like as a hash and some structure construct, and then stuff that in the JVM?
So that's a very, very interesting point that I've thought about. The point is that we could create names of types based on the structure, like a hash of the structure, and then nominal typing becomes structural typing. You can do that, sort of. You start to run into problems with separate compilation and class loading, but if you have just one class loader on the JVM, and you're sure that your hash algorithm is consistent and unique, then you can do it.
If you don't generate too large names or anything like that.
Yeah, your names have to be small, and you might, as a practical matter, you might run into permgen issues. So.
But you could also run into a logical problem because, let's say you have two different types that are, has, length. They're different kind of length, or draw. It's a different kind of draw, and you suddenly assume that these two types are really the same because their structure is the same, but they're logically not. And so, there shouldn't be an automatic assumption.
That's the argument for nominal typing right there.
Yes, that is exactly the argument for nominal typing. So you can have two types with the same structure that aren't actually the same type, but you just put them together and suddenly you assume they're the same. That is perhaps a disadvantage of structural typing. I don't know. Is that something the type system should care about? I'm not sure. So we've actually run out of time, but I'm happy to continue taking questions here. So just no aspersions for milling out of the room if you want to.